what you're looking at is this divisibility, and I promised Min that I was going to blow his mind with this topic, and you're going to say, this does not seem even remotely interesting, but watch out. This is going to get good. So all he said is when we said that A divides B, we said that B was equal to what? K times A, right? So A times K is equal to B, or sometimes we reverse those, okay? But what Gauss is saying is if it's not divisible, we end up with what you and I call a remainder, and he had a little bit different name for it, but congruent module M means that if you look at this not being divisible, you end up with some kind of a remainder, right? So if it's divisible, if it's not divisible, it's going to be this plus a remainder. Well, if you took this A is, let's see, how would we best show that? If you said that this thing is not, you could say that B minus R is equal to KA. Is that correct? And so could you say that A divides B minus R? Could you say that? And yes, you could. And so this is what we call a module, or there's a whole bunch of values that will work for this. And this is how we get our calendars, when's, is this day going to be on a Monday or a Friday? So when we talk about congruent, what we're saying is M divides A minus B. And the way that he wrote it, his notation, is A is congruent to B mod M. And so we're going to get some terms in here. And the terms that we're going to get will be, first thing, here's the form that you want to remember. Just one more time, M divides A minus B. So A minus B is equal to M times K. A is equal to B plus MK. This is pretty much in a nutshell what this is about. And so then what you could do is you could say A is congruent to B, okay, mod M. A is congruent to B with any multiple of that remainder times M. And we'll talk about what numbers are divisible, and it'll make perfect sense. Let's take a couple. So let's say we have, 1 mod 2, or 1 is congruent to, let's do an even easier one. Let's do mod 2. So what's 5 divided by 2? 5 halves, or 2 and a half. What would be the remainder of this if we divided it? 1. So 5 is congruent to 1 mod 2. Is 3 congruent to 1 mod 2? Sure. Is 1 congruent to 1 mod 2? Well, here's what you do. You say 5 minus 1 is equal to 2k. Is that true? Is 4 equal to 2k? What would k be? 2. Is 3 minus 1 equal to 2k? 2 is equal to 2k. What would k be equal to make this true? 3 minus 1 equals 2k. What would k be equal to? 1, right? How about 1 minus 1 is equal to 2k? What would k be equal to? 0, to make it true. So when we're looking at congruence, these are congruent to each other if you can just take, and they used A minus B is equal to m times k. Congruent in what? And equal, good, is that we're not saying 5 is equal to 1, but we're saying that 5 has the same remainder 1 when you divide by 2, as 3 has the same remainder of 1 when you divide by 2. All right, a couple of things that you need to see. One is there's 3 different, we're going to look at this third quarter equivalence relation. These 3 have to be true for this to, congruence to work. If you look at A congruent to A mod M, that's called the reflexive. That one's super easy to prove. A minus A is equal to K times M for any M if K equals what? No. Yep. 0. Yep. And then for symmetric here, you have A minus B is equal to K times M. And here we have B minus A is equal to K times M. Let's say, and I used an example here because I got myself into trouble when I used the wrong example. 11 and 3. So is 11 congruent to 3 mod 8? Yeah, because you could say if you divided 11 by 8, the remainder would be 3. Is 3 congruent to 11 mod 8? Yeah, look at this. If you go 3 minus 11 equal to 8 times k, this is equal to what? Negative what? 8. So that works. What is it up here when we go 11 minus 3? Is that equal to 8 times k? What would k have to be this time? 1. So it works either way. That doesn't work for any pair of numbers, though, like 2 congruent to 3 mod, let's try 7, and I hope this doesn't work, is 2 divided by 7. Well, that isn't even true at all, right? So, you just can't put any 2 numbers in. They have to actually, one of them has to work, and then you reverse them, and it'll work. So that's symmetric, and then transitive. That one's kind of easy. If you go A is congruent to B, that's going to be B minus A is equal to Km. What would B congruent to C look like? Tell me what that mathematical sentence would be. B minus C is congruent to K2 times M. Now, if you added these up, actually subtract them. I'm going to subtract these. You're going to get B minus B is 0. You're going to get C minus A is equal to K1M minus K2M, right? And M is going to be K1 minus K2 times M. These are both integers. And then what does this say about M and C minus A? M divides what? C minus A. So then what you could say is that C is equal to A plus Km, and there's your congruent statement. So we can do reflexive, symmetric, transitive, And then what you're going to be doing with these is you're going to, they prove these. Here's how they prove that one. The residual class is module M. You can have multiples of M equal to 0. That's if there are multiples, like Monday to Monday would be a module of M, or of 0. These are, residuals are the same as remainders. Yeah.
So in the example there.
All right, so remember that the residuals, okay, that's your remainder. And they prove this using strong induction, but that's really kind of a definition of looking at A is the number and R is the residual. M is your module. So for congruent modules in equivalence classes, you're going to need reflexive, you're going to need symmetric, and you're going to need transitive. And that's going to come up in March, but for right now, we're good with that. Notice how this looks a lot like the division algorithm, and I think we're ready for the good stuff. Are you ready for the good stuff? Modular arithmetic, there are a whole bunch of things that we can do, and let's just do a couple of easy ones. 19 plus 14 mod 8. So let's say you're going to add these numbers together, and what is 18 mod 8? Or 19 mod 8? 8 times 2 is what? 16, right? So we can play around with these residuals and say, this 19 really is the same as 3 mod 8. And what's 14 mod 8? Yeah, you could say 6. Or you could even say minus 2 if you wanted. Right? And so mod 8 speaking. So if you do that, 3 minus 2 is the same as 1 mod 8. Now, if you took 19 and 14 and you added it up, you get 33. That's really close to what multiple of 8? 32. So how much larger is it? It's 1. But see how this playing around? And this is the part that I like, is you could do this 50 different ways and get up with the same answer. And this is where the creative part is kind of fun. Take 19 minus 14. So I took this, I like the 19 minus 14. So if we're subtracting this, what happens is that this becomes a 5. And 19 minus 14 is what? Is 5. But do you see how it works with what we were doing? That's pretty cool. Now the multiplication is the part that's probably the most useful, because subtracting and adding is not that big a deal. You do this in your head, be pretty easy. But you don't do 19 times 14 in your head. So when we change these to residuals mod 8, look at how nice this is. This is 3, and then this one was negative 2, right? So this is going to be negative 6. And what is negative 6 mod 8? The same as 2, add 8. And so this is 2 mod 8. And you can get them a whole bunch of different ways. They reduced this thing to 3 and 6. So that's kind of a good way too, but whatever you want to do. These solving ways, these we're going to look at in the future. So that's my introduction to mods. We're going to do examples, and we're going to do a little proving on the next video.